Okay, so here we'll talk about the generation of EM wave. Okay, so in the slides, it just tell you some observation and then just tell you some equation or some formula to describe the EM wave, and actually it doesn't really tell you how can we derive all those formulas. So after these slides, or maybe during the slides, you just accept it is correct, and then I will tell you why it will be like that after the slides. So I will have the supplementary slides to tell you how can we derive the wave equation from the differential form of the Maxwell equation, and we can actually derive the wave equation, which is a second order partial differential equation. And then based on this wave equation, we can find the solution of it, and then the solution is actually the EM wave. So at that time you know why it will be like that. If you are interested in the mathematics, then it will be useful. Or maybe when you learn physics, you definitely want to know why the equation like that. Otherwise, you just have many equations, and then you don't know why. You just know, oh, okay, I can just plug in the variable into some formula, and then you don't know what is actually happening. Okay, so here he will talk about some observation about the EM wave. So it means that there are some observation. So the first one is the electric and magnetic field E and B are always perpendicular to the direction in which the wave is traveling. Okay, so here we assume that maybe for every point P in the small figure, we have point P. Then it means that you assume the EM wave is propagating out of the page with a dot. So it's out of the page. And and actually the E field is perpendicular to the propagation of the EM wave. Also the B field are perpendicular to the propagation direction. Also, E field and B field are perpendicular to each other, which is the second point. The second point. E field is always perpendicular to the magnetic field. Also, E field and magnetic field are always perpendicular to the direction of the wave. So in the figure, it is like the EM wave is propagating out of the page, and E field is always pointing upward in this figure, or upward or downward. And then if E field is pointing upward, B field point to the left side. So you can see this one. And then if E field pointing downward, then B field always point to right side. Okay. In that case, it will satisfy the right-hand rule. It will satisfy the right-hand rule, which is the third point. The third point tells you that the cross product E cross B always gives you the direction of the wave travels. So just say for figure A, okay, you have E pointing upward, B pointing to the left. So you have E cross B, and then your thumb pointing out of the page. So E cross B is the direction of the EM wave. And let's say for E, E is pointing downward and B is pointing to the left side. So E cross B, serial thumb is pointing out of the page. That's why I say when E field pointing outward, B field pointing to the left side, and then E field pointing downward, and then B field pointing to the right side. When the wave, the direction of the wave is pointing out of the page. Okay, so it must satisfy the right-hand rule. And unfortunately, there is two moments that both E field and B field are zero. They will be maximize together and they will be zero at the same time. Okay, so the field are always vary sinusoidally. Moreover, the field vary with the same frequency and in phase with each other. In phase means they are maximized together, minimized together, and being zero together. Okay, so yeah, so it just tells you that E field and B field will satisfy this equation. This is the magnitude. This is the magnitude of the E field and B field, and then it will be sine or cosine. It will be just fine. It depends. But if E field is sine of kx minus omega t, then B field should be the same thing. Should be also sine of kx minus omega t. If E field is Em times cosine of kx minus omega t, B field should also be Bm times cosine of kx minus omega t. So as much as they are in phase, so this should be the same. It can be either sine or cosine. Of course, in the textbook, it just wrote, it just write sine of kx minus omega t. Okay, so here, inside the argument of sine, so we have omega t. I think you should be familiar with this. Omega is the angular frequency, 2 pi f. Omega is 2 pi f. And then t is the time, so nothing special. And then x is the displacement. X is the displacement. We assume that the EM wave is so-called a plane wave. It's so-called a plane wave, which means that it only relates to the x-axis. X-axis is the propagation direction. So we just assume that it just related to the x-axis. It doesn't look like a curvy line or a spherical surface. We just assume that x is far away enough, then the ray front, these are so-called the ray front. Ray front, 波前. Ray front, okay. Yeah. So it only relates to x. It doesn't relate to x, y, and z. And the remaining variable is k. K is called a wave number. K is called a wave number. And so k should satisfy 2 pi over lambda. 2 pi over lambda. I will let you know why it will be like that by solving the wave equation. And actually, one thing you can pay attention is that inside the sine, it should be something that has no unit, that is dimensionless, which means that omega times t, omega is radian per second, and then t has the unit of a second, so second and second cancel. Radian is actually not a dimension. Radian is just an angle. So we can have sine of an angle, but an angle does not have any dimension. Okay, so here, as much as k times x should have no dimension, and the SI unit for x should be meter, which means that k should have a dimension, have an SI unit of meter inverse. Okay, so this is called the wave number. So the idea is like in 1 meter, how many waves you can count. So which is actually the wave number. Lambda is actually the wavelength. So which means that k equals 2 pi over lambda. It becomes kx becomes 2 pi over lambda and then times x. Okay, so which means that if we have x to be 1, then you can see how many waves are there? How many waves are there in 1 meter length? Okay, so just try to accept this is correct, and later I will let you know why. So we have EM, EB, times sine of kx minus omega t. And here, actually, EM and BM are dependent on each other. They cannot be free variable, which means that, okay, they should have a fixed ratio. They should have a fixed ratio here. Before telling that what is the fixed ratio, here just tell you that we have an important variable called the wave speed, or we can call it speed of light here, because EM wave is actually the light. So actually here we have the speed of light, and usually we call it c. So the wave speed, even though it is not the light, and for a wave we have the wave speed, which is the omega over k, which is like, here we have sine of kx minus omega t. Okay, suppose this is equal to 0, and when t equals 0, then we should get just say we have a k times x minus omega times 0 equals 0, or maybe it can be just a fixed phase. This is a real method, or maybe for simplicity we just let it to be 0. Then we can see that if t equals 0, we can solve x to be 0. Then we can see if t equals to t, then omega t should be 2 pi. Then we can see kx minus omega t equals 0. Then this thing is 2 pi, so x is actually 2 pi over k. X is actually 2 pi over k. So which means that in this period, how far it can move, this is actually, just now we know k is 2 pi over lambda. So that is actually within a period, it just moves for a wavelength. So actually here, omega over k is just like, omega over k is just like omega over 2 pi over lambda. Or you can rewrite omega to be 2 pi f over 2 pi over lambda. So 2 pi and 2 pi will cancel. It becomes f times lambda, which is c. So for the light or EM wave, f times lambda is c, or any wave f times lambda is c. But usually for general wave, f times lambda is v, but here it is a EM wave, so we use c for the speed of light. And actually c is 1 over square root of mu naught epsilon naught. Okay. So this, based on, actually we can also try to solve the wave equation, and then we can find out that the speed of wave will be this ratio, will be this expression 1 over square root of mu naught epsilon naught. So the permeability constant and also the permittivity constant is related to the speed of light. Okay, so generally in physics class, 3 times 10 to the 8th power meter per second for the speed of light is good enough. But if you need to learn relativity, 相对论, then you probably need 2.998 times 10 to the 8th. Okay, actually I have remembered. yeah, for 9 digit, it is like 2.997 92458 times 10 to the 8th meter per second, yeah, something like that. Yeah. Just now remember a mobile number like that. Yeah, but actually we won't try to use it even for relativity or modern physics. 2.998 times 10 to the 8th power should be quite enough. Yeah, so just now I've mentioned the amplitude of the E field and B field should have a fixed ratio, and this ratio is also the speed of light. Okay, I will also tell you why it will be like that after the slides here. So during solving the wave equation, we will also get this expression. So just try to accept it at this moment. Okay, so next we introduce another variable called the pointing vector. Okay, so the pointing vector means the rate per unit area at which energy is transported via an electromagnetic wave is given by the pointing vector. So just now we know that E and B is perpendicular to each other. Actually here the direction of the wave is also perpendicular to E and B. And we know E is actually a sine wave. It is like a vector. We can write its expression. B field, we can also write its expression like this. So, and actually the EM wave will carry some energy. So here we can also use a vector called a pointing vector to describe the EM wave, how the energy is carried by the EM wave. So it specifies the direction of the. So actually the direction of the pointing vector is actually the same as the wave propagation direction. Okay, so here it says the direction of the pointing vector S of an electromagnetic wave at any point give the wave direction of travel and the direction of energy transport at which point. So it tells you how the EM wave is propagating, and the magnitude of the pointing vector is the rate per unit area at which energy is transported via the EM wave. Okay, so the definition of the pointing vector is like E cross B. So just now we already mentioned that E cross B is the direction of the EM wave. So yeah, so this direction is correct, and it should be divided by mu naught. So you can regard it as a definition of the pointing vector. Okay, and based on this pointing vector, actually we can know something called the intensity of the light. By taking the magnitude of it. Let's see. Yeah. Because just now we know that EM is actually EM over BM is C. So here, when we try to take the absolute value of S, which means the magnitude of this vector, and we call it intensity of the intensity of the light. Actually, it's actually not the absolute value. It should be 1/2. It should be 1/2. Because here EM, this is the amplitude. This is the amplitude. And if you still remember in chapter 31, we talk about the root mean square value. The root mean square value is actually related to the average power. The average power. So here, in the definition, it's also talking about the rate per unit area which energy is transported. It is like the average power. So actually, it is like, it will have a 1/2 factor here. So when we try to take this absolute value, it is like 1/2, and then here we have an EM, and then also BM over mu naught. EM, BM over mu naught. And in the previous page, we know EM over BM is C, which means that we have a C, or EM over C is BM, and then we try to plug. We just swap BM and C, so we have an EM over C is BM, and then we can try to replace BM there. So here we have 1/2 EM, and then BM is EM over C. So here we have another EM over C mu naught. And then also based on this one, EM is an amplitude. Our ERMS is the RMS value of EM. So we try to split this 2 to the EM, and then finally we will have a ERMS square over C mu naught. Okay, which is the intensity of the light. The intensity of the light. And then by another way, we can also see that if there is the power generated by the source, then it will propagate out like a spherical way. And then each blue circle also specify the ray front of the EM wave. And then as much as it try to transmit the power of PS, and then every wavefront is a spherical. So PS over the surface area of a sphere, which is 4 pi r squared, will be the intensity. Intensity means the power at a single point there. So PS over 4 pi r squared will be the intensity. So the intensity in terms of ERMS is like this, and then also in terms of the power, so we can try to equalize this one and this one, and then we can try to find some relationship between the power and the E field. So here is a sample problem. It says when you look at the North Star or Polaris, so in Chinese it's called 北极星. Okay, so you intercept light from a star at distance 431 Ly is light year, 光年, light year. Okay, emitting energy at rate of 2.2 times 10 to the third power times that of our sun. Okay, so P sun generated by the power generated by the sun is 3.9 times 10 to the 26 watt, and neglecting any atmosphere absorption. So find the RMS value of the electric and magnetic field when the starlight reaches you. Okay, so actually the North Star is more or less close to the north in the Earth, which is not perfectly in the north side, but very close to the north side. And actually North Star, you can see with your naked eye, actually if there are not much cloud, or actually you can see with your naked eye. Okay, so here, let's see. So in the previous page, we have I equals PS over 4 pi r squared equals E RMS square over C mu naught. We just have these two formula in the previous slide. And here R is 431 light year, which is not an SI unit, so we need to convert it back to the SI unit. So R is actually 431. Okay, so we need to multiply it by the speed of light, which is 3 times 10 to the 8th power. Okay, so this is a meter per second, and then this is light year, which is like the speed of light multiplied by a year. So here we have a year over a second. So let's see how many seconds in a year. So we need to multiply it by second to hour is 3,600. So this is 1 day. And then in a year, there are totally 365.25 days. Okay. Sorry, I forgot. Every day we have 24 hours. Okay, so when we try to count how many seconds in a year, so this is 1 hour, and then we have 24 hours per day, and then every year we have 365.25 days. Okay, so this is actually 4.08 times 10 to the 18th meter per second. Okay, so this is, that's why we will use light year for the cosmetic stuff because using the SI unit will be a too big number. Okay, so actually we can calculate what is the ERMS. Find the RMS value of the electric and magnetic field. So that's what we need to find is ERMS. ERMS, you can just move this term over and then take the square root. So we have PS times mu naught C and then over 4 pi r squared and then take the square root. Okay, so here we have 3.9 times 10 to 26 power, and then times mu 0 is 4 pi times 10 to negative 7, and then times speed of light is 3 times 10 to the 8th all over 4 pi, and then times this number 4.08 times 10 to the 18 square, and then take the square root of the whole thing. So ERMS is 1.24 times 10 to the negative 3rd power. Actually, you can use volts per meter or Newton per coulomb. Hope you still remember the SI unit for the ERMS. That's what you still need to know for the what you still need to know before the midterm exam. Definitely I will still ask you what is the E field or the B field, then you need to still write out the correct SI unit. And then for BRMS, or even though we only have a EM over BM equals C, but actually if we have an ERMS over BRMS, which should still be C, because if we just need to divide square root of 2 for both EM and BM, and then they just cancel each other, so it doesn't change the left side. And then this one is ERMS, this one is BRMS. So BRMS is nothing but ERMS over C. So it is just 1.24 times 10 to the negative third power over 3 times 10 to the eighth power, which is 4.1 times 10 to the negative 12 Tesla. Okay, so this is ELRMS, this is BRMS. Okay, so next we just briefly introduce what is the radiation pressure. Okay, I don't know too much about it, but yeah, so why the textbook will just introduce radiation pressure here? The reason is that I think you should have learned something called duality during the high school physics. Okay, so in Chinese this is called 二象性, or more detailedly it is called 波粒二象性, which means that the light or the EM wave have both the property of a particle 粒子, okay, and also 不是料粒 okay, so particle and also the wave 波动. Okay, so sometimes the EM wave have the property of a wave, which just like this one. You can see this one is actually a wave. It's actually a wave. And if you just plug in this E and B to this expression, the Poynting vector is also like a sine wave. Yeah, because it's just like a sine square of something. Okay, and then it is actually just like EM/BM. So it's just like EM/BM and then times 1/2 1 minus cosine of this stuff, or 2 times of this stuff. So this is still like a sine wave. So it's the property of wave. And here it just also have the property of the particle. So it's just like, so considering these two, it's just like momentum. So if the wave is shooting to a surface, and if it is totally absorbed, for example, if it is a black matter, then the EM wave will be absorbed by the matter. Then there will be a force acting on it, which is like if you have a spotlight shooting on you, then you feel like, even though you don't look at the light, then you feel like there's something shooting on you, which is the photon. And if this is totally refracted, maybe it's just a mirror. It's a mirror. Then when the wave is shooting there, and then a wave with the same power should be transmitted backward, then the force will be double. Yeah, it's just like the collision. The collision. Yeah, it's just like it should have a conservation of momentum. So which is a property of a particle. So that's what I can tell you of why we have the factor of 2 there. And later on we don't have too much about this. So maybe we just stop here today.